right, so this is our first video of the semester, and I wanted to give you a little background on waves, which is going to be our first unit that we study this semester. So what is a wave? A wave is a disturbance that travels through a medium, after that disturbance happens. So to me, the picture that I always have in my mind of a wave is like ripples in a pond. So if I throw something in a pond, it makes that disturbance. Say I throw a rock in the pond, it plops into the water, and then you see the ripples follow or travel out away from where the rock hit the water. So the disturbance is the rock hitting the water, and then the ripples are the waves that are traveling. The medium, which is what a wave usually has to travel through, is that material that it travels through. So in that example, the water is the medium. Here is another picture right here of a wave, the idea of how we could create a wave. Again, there's a disturbance. In this case, the person is holding a string, and what they are doing is they give it a quick flick at the end. That creates a disturbance that ends up traveling down the length of the string. And so this is another example of a wave. This could actually be what we call a wave pulse, where it's just a single little blip. And that would happen if a person just kind of flicks the string once. If we had a person holding the string and they continually flick it back and forth, that might be more realistic in terms of the type of waves that we're going to end up talking about, which are traveling waves. So again, in order to have a wave, you have some sort of disturbance, and then you also have a material that wave is going to travel through. Eventually, when we finish up our unit on electricity and magnetism, we will be talking about electromagnetic waves, and those specific types of waves can actually travel through a vacuum. So that would be one type of wave that does not need a medium to travel through. Now, the interesting thing about a wave is that as it's traveling, it is carrying information with it and carrying some things with it, but the material itself, the medium, is not traveling with the wave. The medium moves as the wave travels through it, but it's not traveling in the same direction as the wave goes. And just to introduce a new word that you actually see over here, a lot of times we're going to say the propagation of the wave, which just really means the traveling of the wave. In any case, what I was starting to say was, as the wave is traveling through its medium, what it will be carrying with it is energy and momentum. There are three basic types of waves: mechanical waves, electromagnetic waves, and matter waves. In this chapter, we will be focusing on mechanical waves, and as I mentioned earlier, when we get to the end of our section on electricity and magnetism this semester, we will actually talk about electromagnetic waves, which are actually light waves. So there are two basic types of waves that we're going to be thinking about, and what makes them different is how the disturbance of the medium is oriented relative to the traveling or propagation of the wave. So our most common type of wave, the one that I think really is how we probably picture waves, would be this one over here, which is the transverse wave. A transverse wave, here you can see this wave is actually traveling in the horizontal direction, but the disturbance is in the vertical direction. And so that's where it gets the name transverse, because the propagation and the disturbance are at right angles to each other. This is similar to the wave on a string that I had in the previous slide, except that it's happening continuously. This woman is holding the end of a long spring, and she will make it go up and down, like move the end of it in a very regular manner, and it will produce this transverse wave that we see here. The other type of wave that isn't as common, or maybe not as intuitive to us, is a longitudinal wave, and in this situation, the disturbance is actually parallel to the direction of propagation. And so here you see again the wave is traveling in the horizontal direction, but this time the disturbance within the spring, which is our medium, is also in the horizontal direction. The way that the woman would create this longitudinal wave is she takes the end of the spring and she's compressing it and stretching it. So she's pulling in and out with it instead of pushing it up and down. What this does, it creates places in the spring where the spring is more compressed, and then alternating with that are areas where the spring is stretched out. And so the stretching and the compressing regions are going to be traveling down the length of the spring as the wave travels through the spring itself. Now, we don't often see a longitudinal wave when we see a picture, but just for your knowledge, a sound wave is actually a longitudinal wave because when sound travels through air, the pressure of the air alternates where it's high pressure and low pressure, and that's the longitudinal wave that is traveling through the air when sound is traveling through the air. So I wanted to show a picture. I'm going to show you a picture of a transverse wave and talk about some of the quantities that we're interested in when we describe a wave. And then we'll switch and we'll look at a longitudinal wave. So once again, in this picture, we're using the idea that a water wave is a really convenient way to to visualize a wave, and it's the way we would visualize a transverse wave. So we have this water wave, and what we've done is, of course, a wave is a dynamic situation. It's a traveling thing. So to really be able to visualize it, we might want a movie. But what we can do is we can take a snapshot of the wave to see what it looks like at some instant in time. So that's what we've done here, is we've taken a picture of this wave. And you can see from the diagram that here they designate the direction of motion or propagation of the wave is in the horizontal direction from left to right. And the disturbance in the wave is what we see is in the up and down direction because it's a transverse wave. The dotted line represents the level of the water that it would have if it was not having a wave travel through it. And right here we see that the water has actually gone down a distance, and this is marked minus A. And way over here on this side we have it, you can see that it's up, the water level is up above that dotted line, and that's a distance A. In both places, the A represents the amplitude of the wave, which is its maximum distance from what we might call the equilibrium position. So we're going to just write that down. A is equal to the amplitude. Another quantity that we would be able to measure from this picture would be the wavelength. And so if we go from this location where this peak is, and we go to where the following peak is, this represents a wavelength. Which we're going to designate by the Greek letter lambda. And so what that does is, if you imagine if I took a segment of this wave that is that length, and I can just kind of paste them together in series, and that will create my total wave. So it's a distance that's measured from one peak to the next peak, or from one trough to the next trough. The troughs are the low points, and it represents sort of the complete oscillation pattern that we see for the particular wave. And finally, one last thing that's kind of interesting and that's illustrated in this picture, but we might not really realize it, is this little seagull here. So what's the point of the seagull? This is actually helping to reinforce the idea that as the wave is traveling through the water, it doesn't actually carry water with it, because what they're trying to illustrate in this picture is as the wave passes by the seagull who's just sitting on the water, the seagull just bobs up and down. He doesn't actually move from left to right with the wave, he just bobs up and down as the wave travels through the location where he is. And so that's an important thing to understand. Notice that the total displacement that the seagull will undergo will be twice the amplitude, because he'll go up a distance of the amplitude, but he'll also fall down the distance equal to the amplitude. Another quantity that we might want to think about is F, which is frequency. Which is something that that little seagull could count or could determine if he was so inclined, because the seagull could count how many waves pass by his location every second, and that's the frequency of the wave. That would be related to how fast he goes up and down as those waves pass through him. And so these are just some quantities that we might be interested in for a transverse wave. Well, actually, these quantities that I've listed are actually important for both types of wave, but we've illustrated it here for the transverse wave. Now, here's a picture. This is sort of a different illustration, but it's more helpful to look at it this way. This is of a successive sequence of snapshots of a longitudinal wave. And so what you can see as we go down from top to bottom, the time that has elapsed is increasing. And you can see, for instance, remember that we said with a longitudinal wave, when it's traveling in the spring, there are places where the spring will be compressed and then stretched out. And you can kind of see as we kind of go down, this region where the waves are more compressed is sort of moving along through the length of the medium that this longitudinal wave is passing through. And again, here's the velocity showing us that the wave is going from left to right. Now, if we think about how for the picture that we looked at just previously, we had the seagull went up and down, and that was the motion really of the disturbance for the transverse wave. Remember, for the longitudinal wave, the disturbance is in the same direction as the motion or the propagation of the wave. And what they did in this picture is they chose a single point on the medium, and they're actually, as we go down, remember this is with time, we can see how that point, instead of going up and down, is actually sort of going back and forth. So this point on this, say it might be the spring still, goes back and forth as the disturbance travels through the slinky or the spring, if you will, which means that we've sort of bookended this region with dotted lines, and the dotted line on the left represents sort of the one end point of the disturbance, and the one on the right is the other end point, and then down the middle would be like where it was when it was in equilibrium, like where the point might have originated, like as we see up here at t equals 0. And so essentially what's happening is this point, as you look at going down this graph at different pictures, this point on the spring kind of just goes back and forth. That's its oscillation. And you can see down here at the bottom, it does actually have, you know, between the middle dotted line, which is the equilibrium location, it has a maximum displacement on either side of that that is equal to the amplitude. So let's just review some of the different quantities or characteristics of a wave that we want to be familiar with. And so I'm just going to draw the wave again for our reference. We're going to go with a transverse wave. I'm not a very good drawer of the wave, but pretend it's uniform, just picturing a sine wave or a cosine wave. So the first thing that we're interested in is the wavelength. And the wavelength, remember that we designated it by the Greek letter lambda. It is the go here to here. So it's a distance from one peak to the next peak, or it could be from one trough to the next trough. It's just the length of one complete wave pattern. So I can use any points on the wave as long as I get the complete oscillation. This is going to be measured in meters because it's a distance. Then we also talked about the frequency. Remember, we talked about how the seagull would bounce up and down, and the number of complete waves that would pass that seagull per second represented the frequency. So this is actually can be measured in 1/seconds, or we might use the unit we call hertz, which is basically just a name for the unit of 1/seconds. And finally, the last thing that we're interested in about the wave is its speed, which is, of course, just the velocity. And this might be measured in meters per second if we use our typical units. And it turns out that the way that we calculate the speed of the wave is we take the wavelength times the frequency, and that gives us our speed. And that's this equation right here. So how do we describe these waves? So we're going to really be talking about periodic waves, ones that are going to be able to be represented if they're transverse waves by a sine wave or a cosine wave. And so we use the sine function to designate these traveling waves. It's similar to simple harmonic motion, which is what we finished up with last semester. But the difference here is that for simple harmonic motion, we simply had something that was oscillating between two different distances as a function of time, and so we were only really trying to find its position as a function of time. But for a traveling wave, we actually have two position quantities. Y represents its sort of displacement in the transverse direction for our transverse waves, and then X represents sort of the position along the horizontal. So like when we draw a wave like this represents the Y, and this represents the X. Now you might see, but hey, wait, there's a T in that equation too. And that's where things get kind of complicated. To look at the traveling wave, we have to make a choice. We can either look at it at a specific time. So this is like a snapshot. So this graph of Y versus X represents a snapshot of the wave at some time. I don't really know, it could be at any time, but we're taking a snapshot of it. Because then what that does is in this expression, we would put a specific value in for T, and then that just becomes a number that doesn't change. And then what we would want to graph is Y is equal to A times the sine of KX, and then plus these numbers. The other thing is that we might want to know, instead of thinking about what the wave looks like at a specific time, what if we want to know how the wave moves at a particular location? So the graph looks pretty much the same, except notice that our axis has changed. So if we want to draw something static for a wave, we either have to make the choice to take a snapshot of the picture at a specific time and see how the wave varies with the horizontal position, or we have to choose a position in the along the x-axis and look at how the wave, the position of the medium at that location will change as a function of time. So there are two different things that we're looking at here. I know the graphs look the same, but notice how what the axis is being labeled is actually different. Now let's talk a little bit more about the details of the expression here that we see. The other thing that we have to see is you have sine of kx minus plus omega t. So the minus means if we look at the minus sign, if our expression has the minus omega t, we're talking about a wave that's traveling from left to right. If we have the plus sign, the wave is traveling in the opposite direction. So that's one piece of information that we see in there. Of course, A that you see out in front, that's the amplitude of the wave. We've already talked about that. What is K? K we call the wave number. And so basically that's talking about sort of how we go through the oscillations in terms of x. The wave number is equal to 2 pi over lambda. And its measurements, its units is going to be 1 over meters. And so that gives us a sense of, like, on this graph, we know that, for instance, this from here to here represents 1 wavelength. And then we could also figure out from that what the wave number would be. Omega, we see here, is the angular frequency. It's really the same value that we saw with simple harmonic motion. It talks about really how quickly at a point, at a particular location on the wave is oscillating back and forth. We saw last semester that this can be expressed as 2 pi times the frequency, and this would be the frequency of the wave as it was defined that we talked about previously. And then also remember from simple harmonic motion that frequency and period are inversely related. Remember that this is the period and this is the time for one oscillation. If I look at this graph, coming back to this graph of y versus t, one complete oscillation goes from here to here. So that would represent the period of the wave. And so finally, just doing one final substitution, I could express omega as 2 pi over period. You might say that you've seen all those relationships before with simple harmonic motion, and you're absolutely correct. So this is just a little bit of background for waves to get us going. I hope that you find this helpful, and we'll be doing a little bit more with all of these ideas when we get to class.